There are 47 minutes in every lunar orbit where Earth disappears. Not behind clouds, not below a horizon. Gone. No blue, no light, no reference point. During simulation runs for Artemis II, internal crew reports flagged something unexpected. Not fear, not disorientation. A measurable delay in visual processing when the last sliver of Earth slipped out of view. The human brain does not like losing its anchor. The far side of the moon is not just a location, it is a condition. When the spacecraft crosses the lunar limb, radio contact with Earth cuts instantly. No fade, no static, just absence. The moon's mass blocks all direct communication. This is not new. During the Apollo 8 mission, astronauts described the silence as total, but that word was never quantified. Now it has been. A 2024 systems analysis using Orion capsule telemetry modeled internal acoustic feedback during comms blackout. The onboard microphones, calibrated to detect micro-vibrations in the hull, recorded a drop in ambient signal variance by 18%. Not silence, a structural absence of expected noise patterns. The cabin didn't go quiet, it went wrong. Visually, the effect is worse. On Earth, distance is inferred through layers: atmosphere, light scatter, color gradients. Remove Earth from the sky, and those cues collapse. The moon offers no atmospheric diffusion, no haze, no depth softness. Shadows are binary, light or nothing. From orbit, the surface stops looking like terrain. It looks like impact data, raw, unprocessed. There's a moment. Engineers marked it during virtual exposure tests. The exact second Earth vanishes. If you were there, watching it shrink, then snap out of existence, would you keep staring at the empty black where it used to be? Or would you look away first? I want a real answer. Because something else happens after that moment. The brain starts compensating. A 2025 neurovisual study tied to deep space isolation simulations found that when a dominant visual anchor is removed, the optic cortex increases gain, like turning up exposure on a camera sensor. You begin to see more. Not detail, noise, phosphenes, light without source, motion without object. Now place that inside a spacecraft moving at 11 kilometers per second above a surface that reflects almost no diffuse light, with no Earth to stabilize your frame of reference. You are not just orbiting the moon, you are drifting through a field where your own perception starts filling gaps that shouldn't exist. And the data from Orion's test instrumentation suggests something else, something engineers haven't explained cleanly yet. During blackout simulations, slight timing inconsistencies appeared between external star trackers and internal gyroscopic systems. Fractions of a second. Not enough to trigger alarms, enough to notice. Enough to ask a question no one wants to formalize. Is the absence of Earth just visual, or does it affect how we measure position itself? Channel CTA. Calm, grounded. If you stay for this kind of detail, the kind that doesn't get simplified, subscribe. This isn't surface-level space content. This is where the clean explanations start to break. Because the first crew that crosses that line won't just lose contact with Earth. They'll lose the only reference point the human brain has ever trusted. The blackout doesn't begin when Earth disappears. It begins 1.3 seconds earlier. That's the delay recorded between loss of direct line of sight and the collapse of signal coherence in Orion's deep space comm array during late-stage simulations for Artemis II. Not a clean cutoff, a fracture. For just over a second, the system receives data that no longer has a source. Radio waves don't bend around the moon. Not at these frequencies. The moment the spacecraft crosses the far side threshold, Earth should vanish from every instrument simultaneously. Optical, radio, thermal alignment systems. But it doesn't. A 2025 telemetry review flagged a persistent artifact, a residual carrier trace, decaying in a way that doesn't match diffraction models. Engineers compared it to signal persistence in fiber optics, afterglow inside the medium itself. Except there is no medium here, only vacuum. To isolate the issue, the team referenced archived data from Apollo 8. Analog recordings, no digital smoothing, same pattern. A faint continuation of signal past the point of geometric impossibility. It was dismissed in 1968 as equipment lag. It doesn't fit that explanation anymore. Detail layer, instrument integration. The Orion capsule uses a hybrid navigation system. Star trackers cross-referenced with inertial measurement units. During blackout simulations, one specific subsystem drifted, not position, phase alignment. The star tracker, calibrated against fixed stellar coordinates, reported stable orientation. The internal gyros disagreed, by microdegrees, by milliseconds. That doesn't sound like much, until you realize both systems are supposed to be locked to the same physical reality. Human interaction moment, quieter, closer. If two instruments designed to agree, stop agreeing. Which one do you trust? The one looking outward into space? Or the one sealed inside with you? Answer that honestly. Escalation. Pressure builds. Now add the human layer. During extended blackout simulations, subjects reported a subtle but repeatable effect. Not fear, not panic. A shift in temporal judgment. Short intervals felt longer. Long intervals collapsed. One subject was asked to count 10 seconds after Earth signal loss. He stopped at 17, consistently, across multiple trials. There's a term for this in neurophysics, temporal dilation under sensory deprivation. But that usually requires total isolation. Here, it's happening with full instrumentation, active systems, visible terrain below. The only missing variable is Earth. Data spike, unsettling fact integration. A recent preprint tied this effect to reference frame loss. The human brain does not track time in isolation. It anchors it to motion, light, and distant constants. On Earth, that constant is the planet itself, rotation, sky motion, horizon stability. Remove it, and the brain starts free running, like a clock with no regulator. Channel CTA, controlled, steady. If you're still here, you're not watching for spectacle, you're tracking the pattern. Subscribe, because this doesn't resolve cleanly. Cliffhanger, low, unsettling. Because in one simulation run, the system clocks and the human subject didn't just drift apart, they drifted together, away from real time. There is a threshold at 312 kilometers above the far side, not officially documented, but it shows up every time in the data. Below that altitude, the errors stop looking random, they start aligning. During high-fidelity orbital simulations for Artemis II, engineers introduced a redundancy check between three independent systems: star trackers, inertial gyros, and horizon sensors mapping the lunar limb. Under normal conditions, disagreement between these systems is noise, fractional, correctable. But over the far side, at that altitude, the disagreement forms a pattern, not drift, bias. All three systems begin to lean in the same direction, off by a margin too small to trigger failsafes, but too consistent to ignore. It's the kind of error engineers hate most, not catastrophic, convincing. A 2025 reanalysis of Doppler tracking residuals, using archived relay data from Lunar Reconnaissance Orbiter, showed localized gravitational inconsistencies over the far side basins. Mass concentrations. Masscons. Dense regions beneath impact craters, warping the moon's gravity field like buried steel plates under asphalt. But here's the problem. The updated model, refined with Ka-band tracking data, predicts a deviation curve that should cancel out across orbit. It doesn't. There's a residual left over. Small, persistent, unaccounted for. Human interaction moment. Direct, uneasy. If the map says gravity behaves one way, and every instrument agrees on something slightly different, do you correct the instruments, or do you start questioning the map? Escalation, intensity rising. Now combine that with what the crew experiences. At this altitude, the surface fills the entire lower field of view. No atmosphere, no color gradient, just hard contrast. Crater edges look sharper than they should. Depth cues flatten. Distances become unreliable. A ridge 20 kilometers away can look close enough to touch. In simulation environments, pilots began overcorrecting trajectory adjustments, not because the numbers were wrong, because the visuals were. The brain was prioritizing what it saw over what the instruments said. System-level disturbance, tightening grip. And then there's the clock issue. At the 312-kilometer mark, synchronization drift between onboard systems increases by a factor of 3. Still within tolerance, still safe, but no longer stable. Engineers tried isolating variables, thermal expansion, radiation interference, software timing loops. Nothing fully explains the clustering of these anomalies in one region of orbit. A region defined by two things: maximum Earth occlusion, maximum gravitational irregularity. Channel CTA, grounded, quiet. If you're following this, you already see where it's going. Subscribe, because the last piece doesn't stay theoretical. Because during one extended simulation, a pilot made a manual correction based on what he saw, and for 2.6 seconds, the spacecraft trajectory matched a path that doesn't exist in any orbital model. 2.6 seconds. That's how long the trajectory held. Not predicted, not simulated, logged. And then it snapped back. The descent, controlled, factual. The event came from a closed-loop simulation tied to Artemis II guidance software. Manual input was introduced. Small correction. Within normal pilot behavior. The onboard system accepted it. For 2.6 seconds, every instrument, star tracker, inertial unit, horizon sensor, agreed on a trajectory that deviated from all pre-computed orbital solutions. Not by much, but enough that, if it were real, the spacecraft would have been occupying a position space the model says is dynamically unstable. It should decay. It should drift. It should not hold. But it did. Engineers ran it again, and again. The anomaly only appears under 3 conditions: full Earth occlusion, low altitude far side pass, manual correction initiated by human input. Remove any one of those, the effect disappears. That last condition is the problem, because it introduces something no system model accounts for cleanly: perception. Back in 1968, during Apollo 8, there was a moment not included in most transcripts. A brief exchange. One of the crew noted that the stars looked off. Not gone, not distorted, just slightly misplaced. The comment was logged, then ignored. No instrument failure was recorded. No follow-up analysis. At the time, there was no framework to question it. Now there is. If your eyes tell you one position, and your instruments confirm it, but the underlying physics says it's impossible, at what point do you stop trusting reality? Because here's what the latest analysis suggests. Not confirmed, not dismissed, just unresolved. When the brain loses its primary external reference, Earth, it doesn't just hallucinate visuals, it recalibrates spatial judgment. And in a tightly coupled control loop, human input feeding navigation software, that recalibration can become physical. A correction based on altered perception, accepted by the system, reinforced by consistent instrument agreement, because all systems are referencing the same skewed frame. For 2.6 seconds, the spacecraft isn't breaking physics. It's following a version of it, defined by the only observer left inside the loop. Channel C, CTA, calm, steady. If you value this kind of analysis, the edge cases, the cracks, subscribe. This is where the clean models stop protecting you. Because on the far side of the moon, when Earth disappears, there's nothing left to prove you're still where you think you are.